All right, thanks everybody for being here. And after Dr. Bowyer, I am Daniel Moreira, and I'm really glad to be here today. Unfortunately, I could not be this time in person in Hawaii, but hopefully next time we will have the chance to meet in person and exchange our experiences. So as you might have already realized by now, this tutorial is about telling you our experience with improving computer programs that perform visual recognition tasks such as face recognition, iris recognition, and presentation attack detection by getting inspiration and insights on the way of how people do them. And in particular, in this part of the tutorial, I'll focus on reporting to you some methods that you can adopt to observe, to collect, and evaluate how people are doing visual recognition tests. And I will report to you our particular experience with iris recognition task as a case study. Again, this is the tutorial of human-machine pairing to improve computer vision that we are presenting in the 2022 WACV conference. And I am Daniel Moreira. Thanks for being here. So as I already told you, our focus now is on how humans, they do visual analysis. And for doing this study, you need some approach, and this is what we are trying to bring here today. Based on previous literature and our previous experience, we know that a possible approach is divided into 4 steps. And of course, the first step is you have to pick a support problem which you are gonna expose people to and ask them to solve. So possible problems, visual recognition problems are, for example, object recognition, where you're gonna ask people to categorize objects, or face recognition, where you're gonna ask them to give the names of people they know, and also categorize people they might not know. And also iris recognition, which is a task that is less intuitive, or I would say less common for regular people. But after some quick training, they can get really good into this. And this was reported before in the literature. And you can observe their performance and get insights. So once you pick a support problem, next step is you need to select data. And what happens here is that, okay, we are nowadays in this era of big data, and you have large data sets with tera or even petabytes. But yeah, it's not fair with people, with your volunteers that you're going to observe, to present all this data. So you have really to make some selection. First, because people might not have the time to do it. It might be expensive to buy their time for doing this. And of course, they get quickly tired or bored with these tasks. So you have to be mindful about their time and their availability. And because of this, you have to make a smart selection of your data in a way that you're representing real world, and by exposing people to this data, getting important information that will help you to get insights. And based on our experience, what we have seen is that one interesting way, or one interesting thing to consider when doing data selection, is to categorize data into easy samples and hard samples. Of course, this problem of defining what is an easy and hard sample is a problem per se, but you may consider a few different things when doing this. For example, you may consider how hard and easy it is according to whom. So you may consider regular people, or you may consider experts. Or if you don't have this information yet, which is common because you're willing to do the human analysis, so you might not have this information a priori, you can even adopt a computer program and see how this program struggles by doing this. And I will report to you today a case where we used a computer program to categorize some samples into easy and hard, and it seemed to work. And also, of course, you want diverse categories that are representative of the real world. So you have a nice set of different opinions from people, and we will be able to get insights that will be representative of how people behave in real world. After data selection, next step is behavior, is recording people's behavior. So you want to do this, you want to record how they were given their opinions, and what would be their thinking process. And things you might want, based on our experience, you might want to observe is how confident they are. So you may ask this. Of course, you have to define how many levels of confidence you're gonna ask them. You're gonna ask them to give you while answering your question or solving your problem. And of course, you may want to track when they are changing their opinions, if they are changing their opinions, and what might be the things they are thinking and when this happens. And also, you will want to know where they're paying attention to, if you're presenting the visual data for them on the screen, where they are looking at most of the time, and what are maybe their clicking behavior. So these are things that you should record. And then once you've done this and you have the answers, the last step is measuring their performance. So in this point, you're going to measure their accuracy and get to know how many correct trials they got, and where, when they were wrong for which cases, and for which cases they were right, and which cases were easier or harder for them. And also you may want to track their speed and get to know how long they take for doing the tasks. So these 4 steps, they work for us based on our experience as a framework. And I will take this framework to report to you a previous work that I had in the past in 2019, where we published this paper. It was at WACV 2019, where we reported the performance of humans in iris recognition as a study case. And as Dr. Czajka will explain to you after me, we got really interesting insights that helped us to improve some of our computer programs for doing some of these tasks, visual tasks. Okay, so let's start. So keeping on the framework we are proposing, first we have to pick a support problem. Of course, this will be iris recognition. And at the time, there was a motivation for this. So Dr. Bowyer already defined or mentioned iris recognition, so I won't spend time on this. But iris recognition is essentially the problem of given 2 distinct pictures of eyes, you need to decide if those eyes are the same eye and as a consequence, the same person. And for doing this decision, ideally, you should rely on the irises of the eyes, which is the colored part. So this is how it's done for forensics or formal identification based on irises, based on eyes. So essentially, this is the problem. And if you go to the literature, as Dr. Bowyer had mentioned, John Dogmans was the pioneer in showing that iris recognition is possible, and he was at 2006 he had his most cited work where he was able to perform 200 billion comparisons of pairs of irises and decide if they represented the same eye or not. And in his experiments, he got nearly perfect match rates. And at the time in 2019, we got interested in this problem of iris recognition and how humans do it, because what happens is that the John Dogmans method and other methods that are derived from it, they are not really intuitive or meaningful to the regular people. So people who do not have image processing expertise, they struggle to understand what's going on in the process. And it's important because because of this reason, it's not uncommon to see that iris recognition is avoided in, let's say, courts of law and to be presented as evidence to jury, because usually jury, they have people that do not have image processing expertise, and it makes the iris recognition process less prone to be presented as evidence. And we at the time wanted to make it more human friendly. And by doing this, we got more than that, because we learned ways of how people do it, and we were able to improve iris recognition. Okay, once you pick a support problem, next step is how to select data. And yeah, at the time we had experience enough to know that we needed to have easy and hard samples, so people would quickly decide or struggle a little bit more, and then we could get more of their behavior on these different types of cases. And also we needed diverse categories that would be representative of interesting cases. So at the time we made a data selection with 6 categories that you're seeing here. And the first 2 categories were really healthy irises of healthy people, no problems in the eyes. So for these, we had a long experience here in Notre Dame collecting irises. So we had the 2013 cross-sensor iris data set where we had the same irises collected many times in different days and with different devices and sensors. So it was really useful data set for building pairs and showing to people. And for this set, we divided it into easy and hard cases. And how did we do it? So we actually did not have any information a priori of how people find it hard or easy. So we decided to go with Osiris, which is an open source implementation of John Dogmans solution. And the way it works, so you generate genuine and imposter pairs of irises. So the genuine pairs are pairs of iris pictures that depict the same eye, and imposter pairs are pictures that depict different eyes. And by using John Dogmans solution, you get a Hamming distance of the iris codes that his method generates. And this distance, if it is small, it means the eyes are probably the same, the pictures are of the same eye, so you have the genuine pair. And if the distances are large, you have probably an imposter pair. So in the end, if you plot, as you're seeing here, the Hamming distance, you're going to have 2 distributions, one in black for the genuine pairs, which depict the same eye. And as expected, you expect them to have smaller distances, Hamming distances. And you also have distances, the distribution here in gray for the impostor pairs, where you expect the distances to be larger. And by using these distributions, you can select the easy and hard cases. So any easy cases that you may have, as you can see here in green, are the tail of the genuine distribution, the outer tail, where as in this region, what happens here is that for the images that depict the same eye, they have as expected a small distance. So they were easy cases for Osiris, so no big deal. And also on the other outer tail of the distribution of impostor, those are also easy cases because they also represent different eyes, but their distance is large enough as expected. So these are easy cases. And then as in opposition to easy cases, you have the hard cases that might happen in the middle, where in this case, as you're seeing here, for the genuine distribution, genuine pairs, those are the pairs of images that, yes, they represent the same eye, they came from the same eye, but because of some limitations of Osiris or because they are hard cases, the Hamming distance is larger than expected. And conversely, you have the same for the impostor pairs, or where for impostor pairs or pictures of images that represent different irises, the Hamming distances are not as large as expected. So these are the hard cases. So this is how we categorize it, easy and hard cases. And here's an example of an easy case for Osiris. So it's really easy to figure out that it's the same iris. So you see crypts and they are in the same position. So really clear that's the same eye. And here's another example of a hard case for Osiris of the same iris. Yeah. Besides these two cases, we have a third category that we were selecting, which were irises coming from identical twins. And here Notre Dame had previous experience of collecting this data. And what happens for identical twins is that first I need to explain you quickly how irises are formed. So the way irises are formed in the womb when a baby is being formed, they are driven, yes, they are driven by DNA, but they are the outcome of an epigenetic process. So by friction and by folding and by the position in the womb, the same DNA will lead to different irises in different gestations. So in the case of identical twins, which have the same DNA sequences, because there are two different individuals being gested at the same time, what happens is that leads to the formation of different irises. To the point that these irises, they are as different for computer programs like Osiris as irises coming from unrelated people are. So there's no difference. So Osiris is able to tell that the irises coming from identical twins are as different as irises coming from unrelated people. However, for humans, this is not true. Humans have a really hard time, by the way they look at irises, to tell that irises coming from identical twins, they are not the same eye. So this is a case that was really hard for our volunteers in our experiments and easy for Osiris and other programs. And you can see that even though they are different, they have some resemblance in some points that you're seeing here. And for people, it's really confusing when they say, and they really think that it's the same eye. Another type of irises that we added in our data selection were irises that had a large variation in pupil size. And we had this data set already collecting in Notre Dame. Notre Dame has this large experience of collecting data for irises. And this is an example. So the way it was done, so people were receiving, while collecting their irises, different stimulation of light stimulations of different intensities. So it led to pupils that were closed and pupils that were wide open for the same iris. And as you can see here, for humans, what happens with the crypts and other structures that are having the iris with a pupil that is closed and a pupil that is open, the crypts, they change a lot in format in a way that it's really challenging for people to understand and figure out and make the matches. And this is why we kept these in the data set to try to figure out how people perform it. Besides that, we had other two additional categories of irises. One was irises coming from cadavers. Yes, that's what you're hearing. So Dr. Czajka, he had an experience in the past in the Warsaw Technology Institute collecting irises from cadavers, which, contrary to the common sense, they are still useful for doing iris recognition even weeks after death. And so we added in this data set irises that were collected a few hours after death, and the same iris collected weeks after death. Of course, the bodies were kept in morgues and mortuaries, so there was not a huge decomposition, but there was some decomposition in the iris, and we wanted to understand how people and programs were performing in these cases. Besides the postmortem cases, we also had some irises that were affected by disease. This was another data set that was collected in Warsaw too, by Dr. Czajka. And for these irises, we had some diseases like coloboma and cataracts and some other diseases and traumas that had made the iris have a different format or have some different structures that are not common for regular irises, for healthy irises. And we also kept these in the data set to figure out how people perform and how computer programs perform. So in the end, we had as data selection 1,300 iris images. We used a near infrared version, so no color information. And we manually segmented these cases. So we kept only the iris information. We removed the spectral highlights, and we removed eyelashes and periocular information. And these images, they belong to 512 distinct irises coming from 512 individuals. And of course, with these irises, we generated the same amount of genuine and imposter pairs. So for the genuine pairs, we had the same iris depicting two different versions. And we took care that these pictures, they were not taken at the same day, so they were days apart. And for the imposter pairs, we were putting together irises that were not depicting the same eye, but we are not mixing the different categories we have. So we are not making imposters of, let's say, one easy and one hard case, or one pupil dynamic and one disease affected one. So we were not mixing these. So it would not be evident for people that they had imposter pairs. Okay, after data selection, next step in the framework is how to register or record people's behavior. And for this, we built an interesting experimental setup that was divided into 2 sessions. First session, we were simply asking people to decide if for each trial, for each pair of irises, if they were seeing the same person or not. And for confidence, we used 5 levels. So to avoid bias, the software was always starting with the selection of uncertain, like the person has no idea if that pair is the same person or a different person. And for the other cases, same or different, they had 2 levels. Like, so if they decided, okay, it's the same person, they could choose likely or certain, like they are certain of that. And the same for different persons, so likely or certain. So this was session 1. And then they had, after doing session 1, a second session where we were asking them to manually annotate over the pairs of irises what were the regions that they were seeing that were the same or that they were present in one iris and missing in the other. Okay, so focusing on session 1, this is a screenshot of the tool we have developed. So we had 114 people doing the experiments. The age was between 18 and 65 years old. They were not experts in the task. They had a really quick training where we were showing easy cases and showing them how to compare, how they could get hints, and how to use the tool. And for each person, we had 20 trials, what means we had 20 pairs. And we had 10 pairs of genuine cases and then 10 pairs of impostor cases. And we tried to have a balanced set for all the categories, so the same amount of each category. And we were doing a random presentation. So each time we were running the program for showing pairs of irises to people, the sequences were chosen at random. And people on average spent 7 minutes doing this first part of the experiments. It was really interesting. And then for session 2, we had only 85 people that could stay. And for this part of the experiment, we had only the 10 trials. So we selected the 10 trials from 20 before that people provided answers. And in these, on average, they spent 10 minutes. And what we tried to have here, again, was a balance set and also a balance set in terms of hit and miss that they were based on their answer in the session 1. And we are also allowing them, after annotating matching and non-matching regions, as you're seeing here in green and red, if by any chance, by annotating, they have changed their mind, they could like click in a link and change their opinion and select another option among the 5 that we were asking them, same person or not, and the confidence. So they could change their confidence and their opinion. Okay. And if you're interested in the tool for getting the selection and also drawing on the irises, this is available on GitHub. It's for free and you can download it and change and even apply to other tasks. So it's available. And yeah, okay, so this was the way that we registered people's behavior. And then the last part is how we measure people's performance and what performance they got. So with this, I will conclude my part. So first thing is in terms of accuracy. So we compared the people's performance, the volunteers' performance with 3 programs. So we use those IRIS, which is John Dogma's, the implementation of John Dogma's solution. And we also used IRICORE and Merlin, which are state-of-the-art solutions for iris recognition. And you can see here that humans were not better than computer programs for the data set in general, but they had a decent performances around 70% of accuracy. So they were right 70% of the time. But if we break it down in terms of genuine and imposter pairs, so if you focus on genuine pairs, as you've seen here, you will see that for some of the categories we had of irises, people had some hard times, especially for pupil dynamics. So as you can see here, for the irises that had differences in pupil size, the same iris, but different pupil size, people had only an accuracy of 47%, which is below 50%. So it means that if you flipped a coin, you would get better results, probably get better results than getting people's opinions in these cases. Also, another thing that got our attention was for post-mortem cases from the irises coming from cadavers. So you can see that Osiris was really bad, like below 50%. So flipping a coin again was better. Merlin was the same case, and people were better than these solutions. But there's an explanation for this, of course, because Osiris and Merlin and IRICORE, they were not developed for this kind of data. So what happens with the iris of cadavers is that they have some collapses in many cases due to death, and it will probably mess with their iris segmentation modules. So they are not fine-tuned for these cases. Another point is related to disease-affected eyes. So people were much better than the programs. And again, it might be the effect because it might be the effect of the programs not being tuned for this kind of irises. Okay, with respect to imposter pairs, as you can see here, we have a different situation. So programs were perfect all the time, and this is understandable because actually programs are really tuned to not provide false acceptance. So they are really good at finding imposter pairs, and they have some bias towards saying that pairs of irises are not the same eye, as you can see here. But what caught our attention here with respect to how humans performed is that for twins, this is where they had the hardest time. So twins, the eyes are not of the same, the pictures are not of the same eye. For programs, it's clear they were right all the time, but for people, it was really hard to decide that, and they were struggling. All right, another thing is with respect to confidence. So how confident people were doing this. And now I'll show confidence in terms of their answers. So you have here the 5 levels of answers, right? Same person certain, same person likely, uncertain, different people likely, and different people certain. And an ideal graph for here, what would you expect? Because we had a balanced set of imposter and genuine pairs. Ideally, what you would see is having 50% of the answers in black here, right? So genuine here with same person. So people were saying, okay, it's genuine, and I mean, 50% of the time they're saying that they were seeing the same person, and you would see 50% of the cases here, and the other 50% of imposters here. But of course, in real life, and what we observed was different. So what we observed in real was this, so much more complex situation. We had 80% of the cases where people could not define or decide, as you're seeing here. And as you can see here on the side where we're expecting only to see black bars, we saw some imposter case. So people were deciding, for example, here in gray, that for these cases, they were seeing the same eye, even though those were not the same eye. Those pictures were not the same eye. And this happened mostly for the case of twins. So they were certain that the pictures of irises coming from twins were of the same eye, but they were not. And conversely, on the other side, you see a lot of black regions that shouldn't be here. And it shows that for these cases, especially here in different people certain, people were sure for many cases that they were seeing different irises, but actually those were genuine pairs. And it happened mostly for the irises with difference in pupil dilation. So they are really hard for people. So yeah, sometimes people were really certain and really confident with their answers, but they were really wrong. So this is something interesting to see. And also in terms of how session 2 helped and how annotations helped. So this is a question, okay, people in the first session were only given their opinion, then second session they were annotating. Did it help? And overall, as you can see here, yes, in red, the times people were providing annotations, they improved their accuracy. And if we break this down, you're going to see here that for genuine pairs, annotating helped in all the cases. And it even made people get better than chance by with respect to pupil dynamic and disease. So before annotation, they were below 50%, so flipping a coin was better. But then by doing annotations, they got better than 50%. And it was really interesting finding here. And with respect to imposter pairs, it was not so evident that annotations helped, or they did not have as much impact as with genuine pairs. In some cases, for healthy difficult, they even had kind of a tie, and they got worse by annotating. But what is interesting here is in the case of twins, where what happened, the case of twins is really confusing for people. And in many cases, as I'll show you next slide, people were right in the first session, and by doing annotation, they changed their mind and they got wrong. And we had the opposite, like they were wrong the first session, and after doing annotations, they got it right. And this is what you're gonna see here in this graph. So here is the report of how many times for each one of the categories you have in the data set. After doing annotations, how many times when people change their mind, if they change it, how many times in black they worsened their answer, so they were right and they fixed their answer to wrong, so they made it wrong. And then how many times in gray they were wrong in the first session and they changed their mind to the correct answer. So as you can see here, most of the time they improved their answers, and you will see that for pupil dynamic, it was really important to improve their process of annotating and matching the irises. But for post-mortem, even better, because we had no cases of worsened situations. People only improved by annotating the irises of cadavers. But in particular case of twins, it was really confusing. So the amount of worse and improved cases was really similar. And the irises of twins are really confusing for people. And then last but not least, and how do people perform in terms of time? And this is a report of time sessions for each trial. So you can see here for session one, when deciding on the trials, and if you divide them or group them by genuine and imposter pairs, and also by hits or misses, so when people was wrong in black and when they were right in gray, you don't see a difference in the distributions of time. So it didn't matter if they were seeing genuine and imposter pairs or different categories, or if they were deciding that they had hits, if they were having hits or misses, information, the time was the same. And we saw pretty much the same phenomenon for the session two. Of course, the times were larger because they were spending more time annotating the trials, but we saw no difference in the time they were spending. So time seemed not to be an important feature here. So in conclusion, based on our experience, we noticed that people performed better when they annotated the irises. And it was an interesting finding for our sponsors, because they learned with this that they should not only ask people to decide if pairs of irises were depicting the same eye, but they should actually explain why and draw on top of it, and even connect same structures and missing structures, so matching and non-matching. Also, we found out that the most challenging cases to people were pupil dilation. So people are not really, it's not easy for them to understand how pupil dilation occurs, and irises from twins. Annotation helped a lot with pupil dilation, but it didn't help with irises from twins. So twins are really a challenge for people, identical twins. And then we also figured out that people were better than machines than computer programs in disease than disease-affected cases, but it might be the case of training these solutions for these particular cases. But yeah, right out of the box or off the shelf, people were better than these computer programs. So all these, our findings are reported in this paper that you will find here. Again, it was published in WACV 2019. And yeah, with next steps in our tutorial, I was reporting and comparing our performance of humans versus machines. And you're gonna see, starting with Dr. Czajka, ways of we can, instead of making them compete, make them collaborate. So for your attention, thank you.